Hello everyone, my name is Joshua Liu, and we're glad to present our work in collaboration with Dr. John Klaschka at the University of Pittsburgh. Graph-Symbolic VQA with rich visual estimators and no question-answer labels. We have learned previous work on VQA in three fields. End-to-end VQA requires massive vision language dataset for training that has low sample efficiency. Newer symbolic VQA just leverages symbolic representations to simplify VQA into modules, but the report results on synthetic datasets such as cover dataset. Graph-based VQA has not been fully exploited to capture semantic structure with unsupervised story. The most ready work lacks richer visual estimators, but only evaluate hand-select questions. To bridge its gaps, we propose a graph-symbolic framework to detect visual reasoning for a graph-based approach, with a fully modular, extensible, and efficient reasoning algorithm to answer questions in polynomial time. We show competitive domain robust performance on GQ and VQ2 datasets without any question answer training. Our framework contains an interesting parser, question parser, and question answer executor. As for image parser, we have base image graph, which leverage off-the-shelf mask recognition pre-trained on calculated of 80 classes predict object labels. We use several visual estimators to predict object attributes such as colors, sizes, places, actions. Then we construct an image graph by using objects as nodes and spatial relations at edges, of which each node has several attributes. In order to enrich the diversity of base image graph, we use pre-trained fast RCN, pre-trained on OpenImage version 4 dataset for 600 classes to predict object labels. We use algorithm to merge base and large image graph according to the object bounding boxes. To this end, we obtained a more diverse node and a richer image graph, which is critical answering accuracy. We want to further enrich the diversity of edges of the image graph. So we leverage pre-trained VSPNet on visual general dataset that can return a triple, including subject, predicate, object. We use this triple to connect two nodes on the image graph, which enrich the diversity of edges. To this end, we can obtain larger and more real-world node and edges for inference and reasoning if we merge base large same image graph. As for our question parser, we consider it as a sequence translation problem. In other words, we train the encoder-decoder algorithm that translates a sequence of questions to a sequence attack segment we defined. The training dataset of question graph translator is programming generated using question semantic relations in GQ dataset together with our proposed 15 fine-grained text. The whole procedure requires no human annotation. So we can easily construct question graph based on text segments afterwards. As for question answering algorithm, the input is an image graph, a question graph, and output is answer. At the beginning, the algorithm traverses each node on the question graph. And then the check valid assignment on the image graph. For example, the algorithm traverses from node 0 to node 1 and node 2. And regarding node 0, defines the valid assignment node on the image graph, which marked as step 0. So from step 0 to step 1 to step 2, we can find target node on the image graph that used to retrieve answers. For the question, what's the name of a piece of furniture? The algorithm will return the name attributes value of the target node that's answer table. As for quantitative results, our baseline model that uses base image graph achieved very strong performance on GQ VQ2 validation dataset. And each of our advanced models use richer image graph, the same question graph has significant improvements. Our major improvements are contributed by adding sync image graph. And VQ2 show very robust performance and consistent with GQ2, except for numbering questions. This is the end of my presentation. Thank you.